In this video, I'm going to be going through a discrete math final, or more specifically, discrete math for computer science, although some stuff like probability and graph theory is not present. Just going to go through the problems. There's 10 of them. Let's just get straight into it. Starting off with problem 1, it says use logical equivalence laws to show that the following compound propositions are equivalent. So the first one, P implies Q equivalent to not Q implies not P. We're going to simplify the right hand side. So using the definition of implication, we're going to get not Q or not P. Double negative, this is going to cancel out, so we're just going to get Q or not P. We can reorder these because they're commutative, so we have not P or Q, and this is just by the definition of implication again. We're going to get P implies Q. So there we go, we're good there. Now the next one, B, we have P implies Q and P implies R equivalent to P implies Q and R. So we're going to simplify the left hand side. Again, using the definition of implication, we're going to get not P or Q and not P or R. And this looks like the distributive law, so what we're going to do is basically undo the expansion. So we're going to get not P or Q and R, and again, not something or something positive. This is just the definition of implication again, so we have P implies Q and R. Now the last one, C, we have not P implies Q implies R, which should be equivalent to Q implies P or R. So now, again, we're going to simplify the left-hand side. So using the definition of implication, we're going to get not P or, and we're also going to do this inside the brackets, not Q or R. Double negation cancels out. So now I'm going to do a little bit of associative property here. I'm going to move the brackets around since these are all or. So we're going to get not Q or P or R, and again, this is just the definitions of implication again, so we get Q implies P or R, and that is it for question 1. So, problem 2 states, determine the truth value of each of these statements if the domain of each variable consists of all integers and justify your answer. So, the first one, there exists some x for which x squared plus 2 is equal to 0. So let's try and solve this. X squared plus 2 is equal to 0. Subtract 2 on both sides. We get x squared is equal to negative 2. And we have to take the square root of a negative number. So here it shows that x only has complex solutions, not integer solutions. So this implies this is false. Okay. Now the next one, for all x there exists some y for which x is equal to 3y plus 1. Now if we move the y to the other side so that we have x minus 3y is equal to 1, you may notice that this is a characteristic Diophantine equation, ax plus by is equal to gcd ab. So we know this has integer solutions. So there's no problem with not being able to get integer solutions. But the problem is with the quantifiers here. You see, we have for all x there exists y. If we look at over here, the way that they solve for x, we have x is equal to 3y plus 1. We can essentially set y be equal to any n where n is an integer, right? And x will also be an integer. So it works that way. However, given the statement here, if we solve for y instead, then what we get is x minus 1 over 3. And you can't just choose any integer x such that you get an integer y. It has to be such that x minus 1 is divisible by 3. So yeah, basically here x minus 1 has to be divisible by 3, And so this is actually false. If it was instead for all y there exists some x, then it would be fine. So the next one, C. So for all y there exists an x such that y squared is greater than x. So let's consider a certain case. We need to, at least one of them has to be true, right? So we're gonna let x be equal to -1, and then from this we have -1 squared is greater than -1. So we have 1 is greater than -1. And so since y squared is always greater than 0, this is going to be true, because any of the negative integers, if you use those, y squared is always going to be positive, the x is always going to be negative, so all of those are going to be true. The positives, that's not always true, but for the negatives, yes. So that works out. Now moving on to problem 3, we're going to do 3a first. It says, use a proof by contraposition to show that if m and n are integers such that m plus n is odd, then m is odd or n is odd. So what we're going to do first is assume that this is not true, that m or n is odd. This implies that m and n are even, and when we add two even integers, so let's say 2a plus 2b, this is equal to 2 times ab if we factor out the 2, and this itself is even. And so with this we have shown that if it's not true that m or n are odd, then m plus n is not odd. And by contraposition, right, I'm just going to use acronym, by contraposition, that means that we've shown if m or n is odd, then m plus n must be odd, right? So we basically looked at the opposite cases and then again took the contrapositive negation, and so that would mean that the contrapositive has to be true. So there we go. Alright, now for 3b, it says use a proof by contradiction to show that the square root of 2 is an irrational number. So what we're going to start off with is we're going to assume that the square root of 2 is rational, and so with this, that's where we should find your contradiction in the midst of the proof. So if root 2 is rational, then that means that root 2 can be written as the ratio of two co-prime integers a and b. Co-prime, that means they're not prime on their own, but pairwise in relation to each other, they only share a factor of 1. That's basically what we mean by reduced fractions. The ratio is of co-prime numbers. And so with this, we can square both sides, so we get 2 is equal to a squared over b squared. And then we can multiply both sides by b squared, so we get a squared is equal to 2b squared. And now you see this is even, so this means that a squared is even. And if you know about this proof also, that a itself is even, right? Because an even number squared is still even. So now if we have this, what we're going to do is let a be equal to 2c, where these are all integers. So now with this, we're going to sub this back in. We're going to have 2c squared is equal to 2b squared. Distributing the power, we're going to get 4c squared is equal to 2b squared. And then we can divide both sides by 2. And then we get 2c squared is equal to b squared. And once again, this is an even number. So what we get is b squared is even. And then that also means that b is even. And this is our contradiction. So if a and b are even, both even, then they cannot be co-prime, right? Because they at least share a factor of 2. And so this implies that the square root of 2 is irrational. And that's it for the proof. Moving on to problem 4, we're going to do 4a first. It says, find the power set of the set A is equal to 1, 2, 3, and 4. So the power set is just the set that contains all subsets of A. So we're just going to write all these down and then formulate it at the end. And we're also going to use some counting to keep track if we have all the possible subsets for each amount of numbers that we sort through. So we're going to write our subsets. So first, all of the single digits. So we're going to have 1, 2, 3, 4, and so with this is basically from 4 choose 1 being equal to 4, and we got all 4 of them, so there goes that. Now for two numbers, 1, 2, 2, 3, 3, 4, and in between now 1, 3, 2, 4, and then beginning and end 1, 4. And so with this, what we basically have is 4 choose 2, which is 6, and we got all 6 of them. Now for 3 digits, or 3 numbers, we have 1, 2, 3, then 2, 3, 4, then 1, 3, 4, and 1, 2, 4. And so with this is just 4 choose 3, which is also 4, and we got all 4 of them, right? And last one, 4 digits, 1, 2, 3, 4, and this is essentially just 4 choose 4, which is of course equal to 1. And don't forget, everything's a subset of the empty set. The empty set is basically 4 choose 0 is 1. from here. And basically, so for subsets, it should be 2 to the n, where n is the cardinality of the set. For here, n is 4, so we should have 2 to the 4, which is 16 subsets. So if we count here, 4 and 6, that's 10. Then we have another 4 and a 1, that's 5, makes it 15. And one last one from the empty set, that's 16. So the power set of A is equal to the empty set 1, 2, 3, 4, and you can do your rest yourself, but you get the idea. You just put them in, plug them in. Alright, so for 4b, it says let A and B be sets. Prove, without using a Venn diagram, that the complement of A union B is equal to the complement of A intersected with the complement of B. So we're going to let X be an element of A union B complement. This means that X is not an element of A union B, and the union is just all the unique elements from A and B. And so this means that X is not an element of A, and X is not an element of B. However, X is an element of the complement of A and also the complement of B, and so that means that X is an element of the complement of A intersected with the complement of B, because if X is both part of these, then it's also part of their intersection, because that's all of the same elements basically. And so therefore A union B complement is equal to A complement intersected with B complement. Alright, now for problem 5, we're going to do 5a first. It says consider the function f mapped from r plus to r defined by f of x is equal to 1 over 3x plus 1. 5a asks, prove that f is 1 to 1, or essentially injective. Also, quick note, they define r plus as the set from 0 to infinity, but 0 is included for some reason. I don't know, that was the distinction they made there, but normally 0 isn't considered exactly a positive number. But anyways, so if we want to prove that this is 1 to 1, what we're going to start off with first is assume that f of A is equal to f of B for all A, B element of R plus. So now we're going to have 1 over 3a plus 1 is equal to 1 over 3b plus 1. Cross multiply, we get 3b plus 1 is equal to 3a plus 1. Subtract 1 on both sides, so we get 3b is equal to 3a. Now we divide by 3 on both sides, so then we get b is equal to a. And so from this, f of a is equal to f of b, and a is equal to b. Thus f is injective, or 1 to 1. Right? If a wasn't equal to b, then that means that it wouldn't be injective. Alright, now 5b asks, prove that f is strictly decreasing. So from this we know that f prime of x has to be greater than 0 for all x element of R plus. So f prime of x is going to be equal to the derivative of 1 over 3x plus 1 and this is just equal to negative 3 all over 3x plus 1 squared. And so now we're going to check f prime of x is less than 0, and so I'm already going to factor this out. Basically we have a negative and then 3 over 3x plus 1 squared is less than 0. So you see here on the inside 3 is positive, and then the denominator, which is a square, is also always positive, and then this is all multiplied by a negative. So that means that this is always negative, right? F prime of x is always less than 0. Thus, f of x is strictly decreasing. And that's it for that one. Moving on to problem 6. For 6a, it says, let f and g be functions from R to R defined by f of x is equal to 2x minus 1 and g of x is equal to x squared plus 1. And they want us to find the composition of the functions f composed with g and g composed with f. So this is relatively simple. First, f composed with g, we have 2 times x squared plus 1 minus 1, which is equal to 2x squared plus 2 minus 1, which is equal to 2x squared plus 1. We do those lines a little better. Okay, now for g composed into f, we have 2x minus 1 squared plus 1, so we get 4x squared minus 4x plus 1, and this is just equal to 4x squared plus 4x plus 2. And it's really up to you if you want to factor out a 2, but yeah, there you go. Okay, now for 6b, it says let n be an odd integer. Prove that the floor of n over 2 is equal to n minus 1 all over 2. Alright, so we're going to start with floor of n over 2. And so what I'm going to do is subtract 1 and add 1 in the numerator. This won't change the value. We can just do some manipulation here. So we have n minus 1 plus 1 all over 2. And we're going to split this by addition so that we have n minus 1 over 2 and then plus 1 floor of 1 over 2. This is all floor. And so if n is an odd integer, that has the form 2k plus 1 for k is any integer. So if I take n minus 1, then I turn it into an even integer. So basically, the result of this is already going to be an integer, so we can ignore the floor function. So we're going to have n minus 1 over 2, and the floor of 1/2 is just 0. So there it is. Therefore, for n over 2 is equal to n minus 1 over 2 for odd n. Now, problem 7, we have to evaluate these two sums, starting off with the first one. This is essentially an arithmetic series. There's just no upper bound for n, it's just arbitrary, so we have to find a closed formula. So, for this, what we can do, we can separate by addition and then bring out the constant 3. So we're going to have 3 times the sum from k equals 1 to n of k plus the sum from k equals 1 to n of 2. And so the formula for k equals 1 to n of k as a sum is just n times n plus 1 over 2. So we're going to just take that, multiply it by 3, and then over here, when it's any constant inside the sum, it's just 2 times the upper bound, or in this case, 2 times n. So we're going to have 3 times n plus 1 all over 2 plus 2n. And then if we make common denominator, add this up, this is going to eventually simplify to n is equal to 3n plus 7 all over 2. And that's the answer. Now the next one, this one is essentially a geometric series here, except the lower bound is not 1, it's from 100 to 200. So we're going to have to reset the index, basically. So what we're going to have is the sum from k equals 1 to 200 of 5 times 2 to the k minus the sum from 200 minus 1, right? That's going to be to 99, 5 times 2 to the k. And, oh yeah, I could have factored out the 5s, but anyways, we're just going to bring this in with the formula for the sum of a finite geometric series. We're going to have 5 times 2 to the 200 minus 1 all over 2 minus 1, and then minus 5 times 2 to the 2 times 2 to the 99 minus 1 all over 2 minus 1. And 2 minus 1 is just 1, right? So we can just cancel these out. There are going to be no fractions. And so this, we can factor out a 5 times 2, which is a 10. So then we have 2 to the 200 minus 1 minus 2 to the 99 plus 1. So minus 1 plus 1, these cancel out. So the end result is 10 times 2 to the 200 minus 2 to the 99. And there's no good way to simplify that. These are just large numbers. And there we go. That is it for question 7. On to problem 8 now. The first question says, let a, b, and c be integers with a not being equal to 0 such that a divides b and a divides c, and we need to prove that a divides b plus c. So if we have this, we have b plus c all over a. Well, since we have addition on the numerator, we can split the fraction by addition. So we have b over a plus c over a. And so we know that a divides b and a divides c. A divides c. So the result will be an integer, and then this implies that a divides the entire fraction b plus c. Alright, now 8b, this one's a little bit more difficult. It says find the last digit of 237 to the power of 1002. So there is a little pattern for these kind of a large number of powers. If you keep incrementing it, the last digit always repeats in a certain sequence of 4. So what we can do is first see for which each it repeats by taking 1002 mod 4, right? Getting the remainder here. And so everything mod 4 like this, and you can cancel the first 2 digits over here. So this is basically equivalent to the same thing as 2 mod 4, which is just equal to 2. And now we're gonna consider the last digit of the base, which is 7, because this also has a pattern where the last digit of the base to the power of this remainder that we get over here, the last digit of that result should be the last digit of the entire power given the pattern. So we're going to have 7 squared is equal to 49, and so that means that the last digit is 9. Now we are on problem 9, and we're going to do 9a first. It says, describe the sieve of Eratosthenes and use it to find all the primes below 30. Well, obviously I'm not going to write this down, but I'm just going to say it here. The sieve of Eratosthenes is an ancient algorithm for finding prime numbers less than or equal to some number n, and it basically uses a method where you list out all the numbers and cross certain multiples out based on a pattern. So we're going to see that when we use this in action now to find all the primes below 30. So we're going to list the numbers from 2 all the way to 30. We're starting at 2 because 1 is not a prime number. 2 is the smallest prime number. So we're going to start with 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. So the first thing we do is cancel out all the multiples of 2. And what we do is we start at 2 right here, and then for each count up by 2 we cross that number out because it's going to be multiplied by 2. So we start at 2, 1, 2, there's 4, 1, 2, there's 6, 1, 2, there's 8, and there's 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30. Now we're going to consider canceling out the multiples of 3. So we start at 3, we don't cancel this one out first, but then each next 3 steps is a multiple of 3 that we're going to have to cancel out. So from 3, we go 1, 2, 3, 6, this is already canceled out, 1, 2, 3, 9, 1, 2, 3, 12 is already canceled out, 1, 2, 3, 15, 1, 2, 3, 18 is already canceled out, 1, 2, 3, 21, 1, 2, 3, 24 is already canceled out, 1, 2, 3, 27, and 30 is canceled out already. So now we go to 4, and the thing is we don't have to check for 4 because 4 is a multiple of 2 itself. So that means all subsequent multiples of 4 were already canceled out. So now we check the multiples of 5. So we start at 5, and then we go up for each fifth number, and then we cancel it out. So from 5, we have 1, 2, 3, 4, 5. 10 is already canceled out. 11, 12, 13, 14, 15 is already canceled out. 1, 2, 3, 4, 5. 20 is already canceled out. 1, 2, 3, 4, 5. Here's the 25 that we can cancel out. And of course 30 is canceled out. And then if we check 6, 6 is also a multiple of both 2 and 3. So all of its multiples have already been canceled out. 7, that's normally prime, and everything else would have been at least a factor of 2, if not the rest of the previous numbers along the way. So that means that we can stop the algorithm. And so we circle what we have at the end. So we have 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. And so that's it. That's all the primes below 30. 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. So there we go. The sieve of Eratosthenes is very simple to understand, but also very beautiful and quite extensive and useful. Moving on to 9b, it says, prove that if n is a composite number, then n has a prime divisor less than or equal to the square root of n. So with this, we're going to have involvement with a little bit of a contradiction to help us out, and then some prime number theorem stuff and divisibility. So we're going to start with letting n equal to ab, where ab are integers and ab cannot equal 1, and ab cannot equal n. This is basically the definition of a composite number. Now, without loss of generality, let's suppose that a is less than or equal to b. Now, without loss of generality, that just means that with this choice of a case, it does not necessarily narrow down the generality of this situation. It doesn't narrow down to anything specific. It still applies to the general whole. So with this, we're going to let a be greater than square root of n. This implies that b is also greater than square root of n. And then putting these together, this implies that their product is greater than square root of n squared, which is just n. And here we have our contradiction. Because the individual factors themselves cannot be greater than the number n. So this implies that a is less than or equal to square root of n. Then there will always be some prime number p such that p divides a and p is less than or equal to a. So prime number, obviously, that's just a divisor, right? So it's going to be able to divide a, and then this always has to be less than or equal to a, or more specifically the absolute value of a, but we're operating on integers here. And so if you think about it, because if a is prime itself, then these things are equal. Otherwise p has to be smaller. If p is greater, then it cannot divide a. So anyways, and then with this, p divides a and p is less than or equal to a, then this also implies that p is less than or equal to the square root of n. And so if a divides n and p divides a, then this means that p divides n, where p is less than or equal to the square root of n, and that is it. Finally, on problem 10, we're going to do 10a first. So it says, use induction to prove that 3 divides 2n cubed plus n for all positive integers n. So, as per usual with induction, we're going to start with the n equals 1 case. So we have 2 times 1 cubed plus 1 over 3. This is just equal to 3 over 3, and this of course divides into 1. So that's good. Now, we're going to assume that this is true for the case n equals k, right? Now we're going to have to prove this for n is equal to k plus 1. So we have 2 times k plus 1 cubed plus k plus 1 all divided by 3. Then if we expand this and distribute the 2's and so on, then we're going to get 2k cubed plus 6k squared plus 6k plus 2 plus k plus 1 all over 3. And now, if you may notice, here is our 2k cubed, and here is our k, our plus k. So what we're going to do is split the fraction up by addition to have 2k cubed plus k on one term and then the rest of the expression on the other. So we're going to have 2k cubed plus k over 3, and then plus, well, we can already tell this is going to be able to be divisible because we can factor out a 3 here, so that we have 2k squared plus 2k plus 1 all over 3, right? And these are going to cancel out because it's divisible, and so both terms are divisible. So that means that the case for n equals k plus 1 is true, and the proposition is true. Final question on this. So we have 10b, which says prove by induction that the sum from k equals 1 to n of k times k plus 1 is equal to n times n plus 1 times n plus 2 all over 3. So again, first we consider the case for n is equal to 1. So we have 1 times 1 plus 1, which is equal to 1 times 2, which is equal to 2. Now we're going to use the sum formula. So we're going to have 1 times 1 plus 1 times 1 plus 2 all over 3, and this is going to be 1 times 2 times 3 over 3. The 3's cancel out, we just get 1 times 2, and this is equal to 2. So that one works out. Now we're going to again assume that this is true for, I'm going to use a different variable now because we have k on the bottom here, it might be confusing, for n is equal to m. And now we're going to prove it for n is equal to m plus 1. Alright, so if n is equal to m plus 1, that means that we're going to have m plus 1, m plus 2, and then times n plus 3 all over 3. And then with the sum formula, we're going to add one more term from the mth term. So we're going to have m times m plus 1 times m plus 2 all over 3 plus the next term would be m plus 1 times m plus 2, right? And now we're going to make common denominator and then add these up together. We're going to have 3 times k plus 1 times k plus 2 plus k times k plus 1 times k plus 2. And this is once again all divided by 3. And now you see we have common factors of k plus 1 and k plus 2. So we can factor both of those out, and then all that we're left with is 3 plus k, also known as k plus 3. So k plus 1 times k plus 2, and then times k plus 3 all over 3. And so therefore the formula is proven. And that was the last problem and the end of the final. I hope you enjoyed this video. For any of you trying to refresh on discrete math, or maybe practicing for another final or test of your own, please click like and subscribe if you liked the video, and I'll see you in the next one.